liquid in a container, then pressure at every point in the liquid is the same. That is the content of Pascal's principle, which we worked out on Tuesday. The other thing that we did is what is often referred to as Pascal's principle, and the idea of the Pascal's principle, as opposed to, no, sorry, not principle. What is it called? Anyway, whatever it is, doesn't matter. This is where we did that hydraulic jack problem, where you, using the idea of Pascal's principle that pressure is the same everywhere, that if you apply pressure, a small amount of pressure across a small area, small amount of force across a small area, that pressure will be transmitted all over the liquid, and that pressure can be used to move a relatively large object across a relatively large area. The difference is the amount of compression that you will do and the amount of work you will be able to get on the other side must be the same. So a lot of work has to be done by you to be able to lift a heavy object. But a heavy object can be lifted very effectively by taking advantage of Pascal's principle. So that was the message that we went through. Now that tends to be an important part of a problem. The other thing that we did, which I think is important, and you will find it out today why it's important, has to do with the fact that we worked out this Pascal's law. Pascal's law, if you recall, was the fact that if I have two levels, I have a level P2 and I have a level P1, and this Y2 and Y1, the pressure is P2 and P1, then one can write P2 minus P1 so pressure above versus pressure below. This is the direction of gravity in this case, must be equal to minus rho G and then Y2 minus Y1. So rho here is the density, and so this is mass per unit volume. And that's how you can compute how pressure falls as the height goes up, provided you have some idea of rho. So for example, like the example I gave, if you go up 1 mile, you can convert a mile to meters and multiply it by 10 meters per second square. And if you know the pressures in the two places, you can probably find the average density. If you know the density here, you can figure out the density at some high elevation. So these things are very handy and very useful, but this also is how we measure pressure in our day-to-day lives for weather purposes, which is something I indicated, which leads to the concept of a barometer. So let me just quickly go over the barometer one more time, because the barometer is not exactly super simple. The idea here is that you have a container. In this container you have a liquid, and then you insert a long tube, and the tube goes into the liquid, and basically the liquid will rise in the tube up to a point. Okay, if the tube is long enough, it will not keep going up obviously forever. So suppose the tube is infinitely long, it will not keep going up forever. Even if the liquid is enormous in amount, it will stop somewhere. And the idea is that where the liquid level stops, the pressure here, we call it P2, is very small compared to P1. So one can therefore approximate P2 as roughly equal to 0. Is it precisely 0? Of course not, but it is close enough. It's a very small number. So the pressure here is 0, and this is, let's say, some height y, and this liquid has a density rho. So now we can use Pascal's law to figure out whatever it is that you need to figure out. What, for example, is the atmospheric pressure? So P1 then would be rho g y2 minus y1. And the standard barometer that we use, which is manageable, is the mercury barometer. Mercury is a very, very dense liquid. It's a metal. It's a very heavy metal, very poisonous metal at that. But it's very convenient because for mercury, this thing is 0.76 meters or 76 centimeters. So, or 760 millimeters, whatever you but at any rate, this is well known. So the density of mercury is known, this is known, G is known, and you can from that infer what the pressure is. So whether we have a high pressure system moving in, whether we have a low pressure system moving in, whether we are going to have some problems with weather, it's a very effective way, especially in the old days before we had satellite-based weather telling us a great deal in terms of images. This kind of information was super useful, and it still is super useful. Okay, so having said these things, let me move to a very important principle. This is the Archimedes Principle, which also is something that we deal with when we are dealing with fluids. So what is the Archimedes Principle? The idea of the Archimedes Principle, which dates back obviously to Archimedes, in this case it's a very, very old principle, is that if you submerge a body in a fluid, in a denser fluid, then in the fluid the body will actually feel lighter. That is the idea of Archimedes Principle. And how will it feel lighter? It will feel lighter because the amount of fluid that this object, having gone under the fluid, has displaced, the weight of that fluid will effectively be taken away from the actual weight of the object. That's what Archimedes pointed out, and the idea of Archimedes Principle hence came from there, and it's really tied to the whole idea of Pascal's law itself. So let me draw this just to give you a sense of it. I'll draw it in a very general way, but you can make it simpler if you wish. So let's take some kind of a cylindrical object, if you will. It can be any object. It doesn't have to be a cylindrical object. You can think of any kind of vessel in water, right? I mean, you can think about a ship in the water. So, and this thing is in a liquid, right? This is air, this is liquid. So let's say the density here doesn't matter for now. And let's say you have some force here coming from the atmosphere. We call it F2. And this cross-section area here, let's say, is A. And let's say the length of this cylinder, in this case, is L. And this height, the height by which the amount of the cylinder that's under the liquid, let's say, is denoted by the amount h, the linear. So it's a nicely shaped object, so there's no problem. Let's say the weight here is mg. Mg will be acting downward, and presumably because it's in a liquid, there's pressure and so on. There will be some kind of a force here. Call it F1. Okay, so we can think about the density of the fluid coming into play because that's important, and rho Fl is the density of the fluid. So for water, it will be 1,000 kilograms per meter cubed, roughly, which is the density, roughly the density of water. So in this case, we should be able to apply Pascal's law. So P1 minus P2. That should then be rho fluid. I mean, it's a static thing. Nothing is moving here at this point. Even if it moves, actually, it won't make an enormous difference right now. And we can think of it, because we have called this quantity H, we can think of it as rho fluid times G times H. So we should then be able to write P1A, which is like a upward force F1, minus P2A, is equal to multiplying through by A times H times G times rho fluid. And so this one would be the upward force, F1. And this one would be the downward force, F2. This F1 is coming because of the liquid itself. It'll obviously be applying some kind of pressure everywhere, and so there would be a force involved here. And the idea is that F1 minus F2 then would be equal to A, H, G, rho fluid. Now AH, you see, is the submerged volume, right? Because if you look at it, H is the part that is under. So this is the submerged volume. And this whole quantity on the left side, F1 minus F2, is defined as FB. And this is the buoyant force. Archimedes Principle problems are not super simple. I'm going to give you a few problems. That will be the next homework set, along with mixed in with some stuff I hope to do today. So Archimedes Principle's basic idea is that the thing will float because of the existence of the buoyant force, and essentially it comes out of Pascal's law. So the difference between the upward and the downward force in this case is what is giving you the buoyant force, which is responsible for this thing being able to float. So now, for example, if you have a very, very large object such as a ship or something like a warship, which are almost like small towns, the principle remains the same. The principle remains the same because the part of the ship that is under the water, that is the part that will be responsible at the end of the day for giving the submerged volume. And the submerged volume with the right density and G and the cross-sectional areas involved, and in this case the fluid is water, will be giving me the right kind of buoyant force, and this buoyant force will therefore make sure that the thing doesn't sink. Icebergs are another example, and we know that icebergs are very, very complicated objects, and in fact I was just reading about the fact that there are about 100 scientists of all kinds of specializations from US and UK that will be studying one of the massive ice shelves in Antarctica, which is melting, to figure out how fast it is melting and how to stabilize it, because once that melts out, depending upon whether it takes a decade or whether it takes more than a decade for the ice sheet to melt out, the global water levels, sea levels, will substantially rise to the point that many countries will probably go under. So it's a major project. And what we don't see is how much of that ice shelf is actually underwater and how much of the ice shelf is over water. Enormous amount of it is actually underwater. So, and hence the concern. And how do you know these things? Because you basically compute something like the buoyant force to be able to work it out. So when you go in the bathtub, for example, you sense that your body feels lighter, and again that's because the weight of the displaced fluid is the weight by which your effective weight is being reduced. Okay, so that's how that works. When you float in water, you know that you can put your head down and float in water very easily. Even someone like me who can hardly swim, I can put my head down in the water as long as I don't breathe in water and manage to float. And that idea is the same, because the buoyant force in this case saves me from drowning. The other problem that comes around in this chapter is what is called Bernoullis Equation. Now this is a very interesting equation, and actually it's a very simple equation. So one way of appreciating Bernoullis equation is by considering some kind of a pipe, let's say like this. Through which you have, let's say it's like this, through which you have fluid flow. So let us say that the level here is y1 and the level here is y2, and I have the fluid moving in here at velocity v1, and the fluid is moving there at some velocity v2, and the density of the fluid is rho, and the pressure here is P1 and the pressure here is P2. So this is a little bit different than what you have done so far. You are thinking about the height difference, as you can see. You are thinking about the velocity of the fluid as it goes from. So imagine a pipe that is going from the ground floor to the first floor, or the second floor, or third floor, or the basement to some higher level. So there is a certain velocity here, and there is a certain velocity there, and intuition tells us that the velocity here might be more than the velocity there, because as it goes up, the water flow velocity should go down, right? And also intuition tells us that because gravity is downwards, the pressure below is not quite the same as the pressure above. In fact, pressure above might be a little less than pressure below. So if I were ignoring the motion completely, the V1 and V2 completely, Pascal's law tells us that P1 minus P2 is equal to rho g y2 minus y1. That's what Pascal's law tells us. So I should be able to write this as P1 plus rho g y1 is equal to P2 plus rho g y2. Nothing is moving here. Now, it's interesting to see something which I want you to observe very carefully. What is rho y as a quantity? Rho is density. Y is a height. Density is mass per unit volume. This is the height, and this is meter per second squared. Okay? This is acceleration. So if you think about it, this thing will come out to be, if you do the dimensional calculations, which requires a little bit of thinking, but if you do this, the unit of this will come out to be energy over volume. You can write the unit as energy over volume. Okay? So if this has the unit of energy over volume, that means I should be able to expect pressure to also have the same unit as energy over volume. Again, nothing is moving, okay? It's energy over volume. So it is telling me that in this static fluid, when nothing is moving, the pressure, which is like a potential energy then over volume, right? This quantity here is equal to the pressure above plus the potential energy above. That's what it's telling me. Okay? So what does it remind you of? If it is energy over volume here and energy over volume here, what does this equation remind you of, you think? Huh? Energy conservation, right? So now suppose I let the fluid move, just like I have drawn there. So this is not adequate, right? Because this doesn't have the kinetic energy piece in it. It has only potential energy and pressure. Pressure is new. We are not used to seeing pressure in an energy conservation equation, but this is something new. So what happens is, for a moving fluid, I should be able to then write 1/2 rho V1 square. That would be the kinetic energy over volume plus P1 plus rho GY1 is equal to 1/2 same fluid rho V2 square, let's say density is not changing, plus P2 plus rho G white. So if you look at it, for a moving fluid, that is nothing but a very old friend. That's your energy conservation equation, because it is telling you that the kinetic energy before plus the pressure, which is a newbie, plus the potential energy, the whole thing divided by volume. So kinetic energy by volume, pressure plus potential energy by volume initially is equal to kinetic energy by volume again later, plus pressure, whatever the pressure is, plus potential energy over volume. And this is, as I said, potential energy. So this is an energy conservation equation, and this, by the way, is Bernoullis equation. So now you can see, I hope, why Bernoullis equation is such a useful equation, because it is nothing but a plain old energy conservation equation applicable for fluids. Now you may say, why is it important? Well, let me give you a simple example of why Bernoullis equation is something that we deal with every day, knowingly or unknowingly. For example, let's say you have a pipe which broadens out, okay? So let us say that in this pipe the level is the same, so the y doesn't change. So y2 minus y1 is 0, okay? So the level doesn't change. Both of them have the exact same level. So therefore Bernoullis equation here would simplify to 1/2 rho V1 square plus P1, and that may be here, where the velocity may be V1 and the corresponding pressure may be P1, and in the wider end of the pipe the velocity may be V2 and pressure may be P2. So by Bernoullis equation I should be able to write 1/2 rho V2 square plus P2, because I'm dropping the y piece, right? Because the y piece is the same in both cases. So here basically y1 is equal to y2. So I don't have that piece. So now something interesting happens. Suppose V1 is larger than V2. So this velocity is larger than V2. That necessarily implies if V1 is larger than V2, then to compensate and make the equality hold, P2, so V2 is smaller, so P2 is larger than P1. That may seem like a simple result, but this is the approximate explanation as to why when you exercise, your blood pressure goes down. Because let us say there is not a great deal of height difference between two parts of our body, or even in the same part of our body. So when you exercise, your metabolic rate goes up, so your blood flow goes up. If your blood flow goes up, then this term goes up. If this term goes up, then your correspondingly pressure should go down. And that's exactly what happens in our bodies. So that's why exercise is very good for us, because it lowers our blood pressure, which is something that we develop as a function of time, whether we like it or not. Most of us develop that. And you can have a very simple understanding of this very non-intuitive result, actually, from Bernoullis Equation. So it's very useful in that way. So why is it non-intuitive? Because we would think that if a fluid is flowing very fast, then the pressure in the fluid should somehow be high. That's what naively we would think. Not so. It turns out the pressure actually is lower when a fluid is moving faster compared to the same fluid moving slower, when the pressure actually goes up. So when you are relaxing by the beach, yes?
I was just wondering, at what point is the height measured for each pipe? Is it like the center of the pipe? Or
Yeah.
Is it
You can think of it as center, but it's a weak effect, unless the height difference is large, right? So it's a weaker effect. Even if there is a minor height difference, if you do the numbers, that's why I dropped it. But if there is a within the body there is a height difference, right? So if you consider the blood pressure in the arteries and veins in my brain versus those in my hands, there is a height difference. But nevertheless, this height difference is relatively small compared to the measurable change that would happen in the blood pressure. It can drop by, we know it can usually would drop by a few points, maybe 5 points or something for the systolic and diastolic. So the approximation holds. That's why I just turned off that term. But yeah, it is a little bit more complicated than that when you have a complicated fluid moving. Yeah.
What happens if they have differing pressures throughout the system? How do you calculate that?
Then it is more complicated. Then it is, study of fluids is one of the most complex of sciences, and you can do a very simple. You can do many very simple fluid experiments, and you will probably not be able to explain it with the stuff we know easily. Yeah. So once you start varying too many things you have to get into hardcore computation most of the time to be able to give meaningful predictions and so on. But this is a very powerful law because it gives you a very clear take-home message as to what would happen, for instance, if a fluid is moving faster, its pressure goes down. The other thing that obviously happens is, therefore, when a fluid is moving, the standard melting and freezing temperatures of the fluid will also change, because the fluid is actually different in some way when it's moving. Its properties change. That's the reason why Niagara Falls would never freeze, even in the dead of winter. In fact, in the 25 years here, I've never seen it completely frozen, although there have been claims to that effect in the newspaper. Not so. If you go, you'll see something flowing there. In fact, underneath the ice sheets, there is stuff flowing also. That doesn't mean it'll never freeze, but it means that the temperature has to be really, really low. And I've been out to falls at as low as -15. And I know for a fact that there is quite a bit of flow at -15, -17 in that range. I haven't been out there at -30, but I don't know what happens there. But at really low temperatures, things might change. All right, any questions on this? Okay. So one of the things I want to do now is I want to switch gears. I'll give you some small conceptual problems on these materials, because that's really the level of grasp that I would insist upon on these later chapters right now. Now, Sylvia, you're not paying attention. You're not paying attention. What? Okay. All right. So let us do another simple experiment. I take a container. And put some gas in the container, let's say. Some gas. Now, what gas can be a relatively complicated question for reasons that I'll come to in a moment. Okay, so let's say V is the volume of this container, and that's easy enough to measure because we know the size. And since a gas will occupy an entire container, no matter what the shape or the size of the container is, we know that this gas homogeneously pretty much fills out the whole place. And let us say it's at some finite temperature T, and T is some positive temperature. So we are not worried about what T is. It's some temperature T right now. And let us say that we can actually somehow measure the pressure of this gas. So I can insert a pressure gauge, let's say, into this thing, and this pressure gauge tells me what is the pressure in the gas. Now this is no big deal, right? Because you can measure the tire pressure of your bike or your car very easily by sticking in a pressure gauge. So we all know how pressure gauges are, so that's not a huge surprise for us. So we have a system then of a container carrying some gas at some finite temperature, and we can measure its pressure. Now suppose I ask you that I want to plot how this pressure varies as a function of temperature. So let us say at whatever room temperature this is, the pressure versus temperature data that I have is here, and then I have the idea of lowering the temperature. If I lower the temperature, what do you think will happen to the pressure? Pressure will go down. Do we have unanimous agreement that the pressure will go down? Huh? Go up. If you lower the temperature, pressure will go down. The easiest way to understand this is what is pressure. So you should have a simple understanding of what pressure is. So pressure arises from the fact that these gas molecules are actually moving around at breakneck speed, right? They're not sitting around like you are and yawning like you are. They're moving around. So as these are moving around, they're hitting the wall, hitting each other, and bouncing back. So what happens is that these gas molecules actually exert a tiny bit of force on the wall as it hits the wall, much the same way as I would exert some force on this door if I hit the door, right? That's what they're doing. Ooh. So what happens now is that it is exerting this force per unit area is what is generating the pressure. So therefore, if you lower the temperature, they will calm down, right? They will move less rapidly, which would mean that the pressure would go down. So that's the intuitive reason why the pressure should go down. So generally speaking, then we agree, I hope, that as we lower the temperature, the pressure will start to move downward. This, by the way, is temperature in degrees Celsius. I didn't specify, but right now it's in degrees Celsius. Now, you see, nature is very complicated. Whatever you do in nature, nothing is super simple. So right now it is super simple. As I reduce temperature, the pressure goes down, pressure goes down. This is my 0 degrees Celsius, which is nothing in Buffalo. So it keeps going down. But then what? So one of the problems that we run into is that when you cool down a gas, what happens? It can become a liquid. So we just can't use any old gas, right? Because many gases, as you begin to cool down, will start to cop out and become liquids. All right, so what do we do? Well, does anyone know a gas that doesn't become a liquid very easily? Helium. And we're running out of helium on Earth. Did you know that? We have to go to moon to get helium. And I'm not kidding. That's a serious statement. Moon has a lot of helium. We need a great deal of helium on Earth for most of our studies at lower temperatures, because Earth temperatures are not low enough for many studies. And helium also serves to cool things very effectively. Helium and nitrogen, they're both used. Nitrogen is cheap, but helium is very expensive because there is a very limited supply of helium on Earth. Moon also has a limited supply, but compared to what we have on Earth, it's enormous. So we have to get it from Moon or Mars or someplace very soon. So brace for some space travel to get some cold liquid. Now you see, with helium, you indeed start to keep it as a gas And if you do these experiments, which are not easy to do, by the way, and keep measuring the pressure as you lower the temperature, you tend to see that if it were indeed a gas right up to the lowest point that you can reach, and if you extrapolate, let's say this is the lowest point you can reach in the laboratory, if you extrapolate, it turns out that this line actually meets the temperature axis. Now that's a remarkable result. That's a remarkable result because almost all the elements that we know, other than helium and to some degree hydrogen, but in this case helium is a better candidate, although hydrogen is lighter. For all of them, the pressure seems to vary linearly with temperature. So as you lower the temperature, the pressure goes down. So as long as you keep it in the gaseous phase, what you begin to see is that this behavior is such that it seems to go down in a line. It doesn't stabilize or anything like, things like that don't happen. By the way, just so that you know, right now we can do experiments that take us down to temperatures that are of the order of 10 to the minus 9 degrees Kelvin, as they say. So let me now come to that. So the place where this thing hits this axis turns out to be minus 273.15 degrees Celsius. Remember, we are on a Celsius scale. So that point is minus 273.15 degrees Celsius. Now that, of course, is something we have to find experimentally. We can't really arrive at that number theoretically. But it turns out then that no material can exist at temperatures lower than that, because all pressure would be zero by this argument, and you cannot have a system filled with atoms, molecules, and so on, which don't move at all, and the pressure is completely zero. You can't freeze all motion in the universe for anything. In fact, at the lowest level, you have some quantum scale motion. So anyway, the point is that experimentally one finds that it is not possible to go to temperatures below minus 273.15 degrees Celsius. So if somebody is telling you that this place is so cold it's minus 400 degrees Celsius, you know for a fact that the fellow is bullshitting, because that's just not possible. It's minus 273 and then you are done. Okay? So that's very important to know, which means that we can now define a temperature scale that starts with this natural zero that nature gives us. And this is how the Kelvin scale of temperature is defined. So in the Kelvin scale of temperature, we write T Kelvin, and this is also called absolute temperature. And this is therefore the temperature in degrees Celsius, whatever the number is in degrees Celsius, plus 273.15, because now you have shifted the zero down to minus 273.15. Okay, so this is really very important, because this is the start of this is the reason why you have to start thinking in terms of this natural temperature scale, which is our Kelvin temperature scale. So actually when you do calculations in physics and chemistry, for sure, and actually almost all thermodynamic calculations, engineering calculations, and so on, you oftentimes find that when you write this P versus T, this T is expressed in kelvins and not in Celsius. In fact, if it is in Celsius, you should convert it to Kelvin just so that the behaviors come out meaningfully. So this is one of the points I wanted to make. Now, so what I just said is that in the laboratory now, you can get down to temperatures that are almost as close to absolute zero as possible. How close? Well, 10 to the minus 9 Kelvin. So in other words, this is just 10 to the minus 9 off from 0 degrees Kelvin. That's how cold you can go. So is it easy to do that? No, it is not easy to do that. Why would one want to do that? There are compelling reasons why one wants to do that. And actually the predictions about what happens in matter at this ultra cold temperatures were first done in the 1920s. And the primary part of the prediction was that when you get down to that temperature scale, you get weird states of matter that behave in ways that we can't achieve under normal circumstances or even under pretty cold circumstances. You entered this very, very special condensed state of matter where you have very peculiar properties. The whole system kind of behaves as one unit, and it has physical behaviors that are totally bizarre in a way. In fact, even now, we understand very little and know relatively little about those ultra-cold areas. But you'd be interested to know that at least 3 or 4 Nobel Prizes that have been given in the past 20 years, or 25, 30 years, on these ultra-cold level physics, because we know so little. And many of the predictions that were made in the 20s, 30s, and 40s, they're only realizable now. And even then, by very, very few groups around the world, large experimental groups that have the equipment to get down to these scales to observe matter at this temperature. So, for example, if one wants to build the argument that matter at this temperature fundamentally changes and you can get lower than minus 273.15, is it possible? The answer is it may be possible, but it hasn't worked out experimentally. By all indications that we know, the lowest temperature in the universe that you can get to is minus 273.15 degrees Celsius. What is the temperature just outside the Earth? Who knows? Just outside the Earth. You just get away from the atmosphere and step out into outer space. So if you are taking a ride on one of these Virgin Atlantic rocket ships that is supposed to take off for civilians, they're not cheap. They're about $150,000 a ticket, I think. But you can go. But if you poke your head out, what will happen, you think? No? Come on. First of all, what is the temperature in outer space? What do you think is the temperature? This is a very important point. The temperature in outer space is slightly shy of 3 degrees Kelvin. That's how cold it is. So we are right around here in outer space. So the current temperature of the universe, and this is true not just outside Earth, this is true all across the observable universe that we know of, it is roughly 3 degrees Kelvin, slightly less than 3 degrees Kelvin actually. So it turns out that you can actually measure how this temperature is distributed across the universe. So you can point to different parts of the sky and figure out what this background temperature that you have is. And the images that you see tell you about how the universe cooled from Big Bang. They actually give you precise details of this cooling process.
Is the 3 degrees Kelvin universal across all universes?
Yeah. We know only one universe.
Well, yeah, no, I'm just saying there's obviously
I don't. But if there is another universe which in principle might exist, we wouldn't know its temperature. That wouldn't be the same. It better not be the same. That will be really bizarre. Spooky even. But our universe, our home universe, we don't have a name for it, we just call it the universe, has a temperature of 3 degrees Kelvin right now. So the universe was actually much hotter earlier on. So when the Big Bang happened, the universe was so hot that we didn't have matter the way we have now. It was one combined gigantic soup of stuff. And we don't know how the soup was. We know very little about it actually. So there's certain, and there are real limitations in understanding the soup because there is no way we can get imaged data about that, because the universe, it turns out, was not transparent then. And you need a certain level of transparency to be able to see how, or to be able to predict reliably how the earlier universe was. So these experiments are obviously very expensive experiments. They take a long time to do, and they require enormous degrees of accuracy. So every now and then you find some news and that leads up to a Nobel Prize, but those are deserving Nobel Prizes. Yeah. then things would change, right? So the universe is cooling, obviously. The universe has been cooling steadily ever since Big Bang. So right now, the universe's age is 13.7 billion years since Big Bang. We know that very precisely. We know that very precisely because we know how heavier elements form. Okay? So all elements, the lightest is hydrogen. So everything is formed from hydrogen through fusion processes, which usually takes place inside very hot objects, such as inside stars. So stars are factories that make heavier materials. That's what stars do. And when stars burn out, they explode and they spread that material all over, which is a supernova explosion. But not every star does that, but many stars do, and that's how the heavier elements get spread. Now, the reason why you and I exist is because there were enough supernova explosions to spread all these heavier elements all over the universe, such that wherever we are in the universe, there is enough of the right material to make us. So this material was not made by our sun. Okay? So you and I are actually truly stardust, and that's a very true statement, because without that heavier element, we won't even exist, right? Because that's simply how it turns out to be. So at any rate, the fact is that the observable universe is cooling down as it's expanding from a very hot soup, and we know how it's cooling down. We know how much of what element was there, and from that one can calculate how old the universe is. So that age is very precise. It comes from the abundances of heavier elements, and that was done by Willy Fowler back a long time ago, and he did get a Nobel Prize for that too, because he predicted the age of the universe, which is no small achievement, right? And it checks out. Now, the thing is that all measurements point to the fact that the universe is expanding quite rapidly. In fact, there are measurements that say the universal expansion is speeding up. Now, whether that's true or not is another matter, but these are all going on. So the fact is, as a gas, if you think about it, expands, the gas should cool. So the universe is cooling. So some billion years later, it will be colder than what it is now. We won't be around, but somewhere, some other form of life, if it exists at that time, they would know that the universe is colder than 3 degrees Kelvin, which is what we measure. And this is an absolute energy scale. So if there is intelligent life in some other planet, and there likely is, then they would also arrive at the same scale once they start to look into material properties very easily, right? So the scale is the right scale. There is no second thing about it. So these are pretty interesting things to learn about. I can go on a lot about this whole deal, but let me stop here, because the universe is cooling, and there is an absolute zero, and so on and so forth, and we don't know what will happen to the universe as the universe ages. Probably nor should we predict, because we may not be able to really make measurable predictions beyond a point. Not that it matters anyway, because you and I won't be there. So let me now spend a few minutes discussing the idea of phase changes. Phase changes, this is something that you can actually calculate with, and therefore phase changes turn out to be an important topic. There are two things I'll talk about. One is phase changes, and the other is heat flow. I won't have time to discuss heat flow today, but let me discuss phase changes today, because this is actually something that you can probably relate to. So let's say I have I want to characterize it first from, let's say, gas. This is the lowest density phase. The next higher density phase will be a liquid, and the next higher density phase would be a solid. So if I take a gas and if I cool it down, then I'll get a liquid, and if I take a liquid and I further cool it down, I would get a solid. In most cases, by down arrow after the T, I mean I'm cooling down the system. As simple as that. And if I heat up a system, so if I raise the temperature from a solid phase, let's say I have a slab of ice, we know what happens. This ice will go from the solid phase if I heat it up to water, and then if I keep heating, it will obviously go from water to steam. That will be the gas phase of water. Water, by the way, is not a good thing to deal with because water is very complicated. There are two hydrogen molecules and one oxygen molecule. It's a polar molecule, and it's a bit of a pain to study because it's not the simplest thing that you would expect for us. It's something that is important for life itself, but it's not the easiest thing to study. So it's very easy to understand that if you take a gas and cool it down, you'll ideally go to a liquid phase, and from a liquid phase to a solid phase. And if you do the reverse, you'll go from the solid phase to the liquid phase to the gas phase. We know that. Now, what you may not know is that how this phase change occurs. So this is where, let's say, the phase change occurs. So therefore, I can think about this between the gas and the liquid occurring at some temperature Tb, which may be the boiling point, and the liquid to solid happening at some temperature Tm, which we can think of as the melting point of a solid, boiling point of a liquid. So it turns out that nature does something very interesting. If you take a solid, let's take a solid. If I take a solid, and if I heat it up, if I give it more heat, it will turn out that it will obviously become a liquid. But how it becomes a liquid, this phase change process is non-trivial. So the phase change process here kind of goes like this. As you heat it up, you will find that the temperature of the gas is going up, of the solid, is going up. So let's say you have a slab of ice, to be specific. You have a slab of ice, and as it's heating up, the temperature of it is going up, let's say from whatever low temperature it was, and it then begins to melt. But once it begins to melt, no matter how much heat you give it, its temperature doesn't change. It sits at the melting temperature, 0 degree, until all the ice has been converted to water. And then again it starts to heat up as you give it more heat. The reverse is also true. So in other words, if you have a liquid and you're cooling it down, the temperature will drop over here. As the liquid becomes a solid, it will sit at the same temperature. Nothing will happen. It just goes from liquid to solid. And once it's all done, then it starts to cool down again. So the message here is the fact that at phase changes, the way these systems absorb heat is different than what happens at the various phases. And this is one of the critical areas in which you are typically tested, because this is a place where we can make up plenty of problems to see if students understand and follow and realize how these calculations are done. So let's now introduce this thing a little bit. It turns out that the amount of heat, I'll call it delta Q. Q, the capital Q symbol, is typically used to denote heat. So this delta Q is always proportional to the amount of mass involved. And that's not a surprise, right? We know that, think about global warming, for example. We have a pretty good idea that it is proceeding at a certain time scale. So, and what is the time scale in which global warming is occurring depends upon the amount of ice cover that we have on Earth. So the fact that mass is involved is not a surprise. What we don't necessarily know is what delta Q would be, because the amount of heat needed, we really don't have much of a clue, because it is not really a simple thing to calculate. We also know that delta Q should be proportional to the amount of temperature change. If you put if you put heat in or took heat out, then delta Q should be proportional to that delta of temperature. So therefore, we should be able to write something which is delta Q is proportional to the mass times the temperature change. And therefore, now I can convert this to an equation. So delta Q And normally one would denote this by the letter C, usually capital C, not small c, m delta T. The C has a name, and the name of C is specific heat capacity. So the book actually does a pretty good job of describing all these things, so feel free to consult the book and the worked out examples there just to prepare yourself, because I don't really have the time to go over all of them. But just to give you a sense of numbers, for example, and the unit here is joules per kilogram degrees Kelvin. That's the unit here, okay? The unit for specific heat, that is. So for every substance, the specific heat C, specific heat capacity C would be different. So specific heat capacity therefore depends upon the phase and depends upon the substance. So for example, the specific heat capacity for ice, sea ice, turns out to be 2.01 times 10 to the 3, so roughly 2000 joules is the amount of heat you need for 1 kilogram of ice to raise its temperature by 1 degree Kelvin, or lower its temperature by 1 degree Kelvin. You have to give that much heat or take out that much heat from there. So as you can see, this amount is what you need to convert from ice to water. But you see, for water, seawater itself is quite different. In fact, it's about twice as much, more than twice as much. It's 4.19 times 10 to the 3 joules per kilogram degrees Kelvin. In other words, what I'm trying to tell you is that water can absorb a lot more heat than ice can. So ice covers that we have are necessarily fragile because they melt more easily, because the amount of heat, energy needed for losing ice is relatively low. It's less than half of how much is needed to warm up water. So water can absorb a lot more heat. And of course, water motion is very complicated, which is the reason why there is a great there are great instabilities in the atmosphere that have been arising from the warming effects that we don't really know about a great deal, and we can't predict very effectively at this stage. So that's what happens when you are in a given phase, gas phase, liquid phase, or solid phase. But it turns out that when you go through a phase transition itself, through the phase change point, then the amount of heat absorbed, let's call it delta Q or Q, it doesn't matter, is dependent upon the mass involved and some other quantity. So at the melting point, this constant is called the latent heat of fusion. And likewise, at TB, and observe that there is no temperature delta T here, because at the phase transition point, there is no change in temperature. So while the whole phase transition is happening, the temperature remains at TB or TM. So this is at TB, and this is at TM. TM being the melting temperature. And this is the, what did I do? This being the boiling temperature, I'm sorry. And this L is called latent heat, as I said. So the two processes are different, and I'll give you things to calculate, because with these formulas you should be able to calculate how much heat is being absorbed as something goes from a liquid phase to a solid phase, blah, 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 at the various phases, during phase change, and all of that. With that, let's move over to the quiz. It's about 10:33. So